All right, so we're going to put some of these properties to use today. So this one says pH of a solution. pH of a solution is a measure of its concentration of hydrogen ions. The concentration, measured in moles per liter, is written as H plus. You'll see it in the formula there, and it's given by this formula. So if you do log of 1 over H plus, this gives you what's called the pH. You've probably heard of pH before. It shows the level of acidity, essentially, or basic of how acidic or basic something is. And again, this is how many hydrogen ions it has, which is really what defines its pH. So we end up with this pH scale, and usually certain things have higher or lower pHs than others. Okay, 7 is your completely neutral pH, if you're curious, which is why like a healthy lake is pretty close to 7. These things then are getting more acidic as you go down. All right. So what's this say? What's the concentration of hydrogen ions in the acid rainfall? So right here we know acid rain is 4.5 pH. So if we plug that in, we would be looking at this. I'm just going to write it as H plus. I'm going to leave the little brackets off it. So we could write this equation, and we would want to solve this for H plus. Now, there actually are a few ways to do this, but kind of considered the best way is to do what we just learned, is to rewrite this as a subtraction problem. So this would be log 1 minus log H plus. From here, I think I would add this log over and subtract the 4.5, just because that kind of cleans it up a little bit. It makes everything positive how we want it. So this is then just log 1, which is going to be, actually, I might as well type that in. That's just going to be a decimal. Sorry about that. So log 1 is 0, which actually does make sense, because this is going to be just 0. And then we subtract the 4.5 over. Okay. So what we're really just dealing with here to kind of clean this whole thing up, log of H plus equals negative 4.5. And now, how do we answer this? Well, remember log is base 10. So as we write this in exponential form, 10 to the negative 4.5 equals our H plus. So that can go in your calculator. It's going to be a real tiny decimal. Or sorry, not a really tiny decimal, but a pretty tiny decimal. So 3.16 times 10 to the negative fifth. So you can go scientific notation here. Probably makes the most sense. If you want to write the decimal out, you could do that too. So this is going to be, I'll just say 3.16 times 10 to the negative fifth. And now again, that's the concentration. This is, if you look at it here, this is in moles per liter. So this is how many moles, the moles per liter of hydrogen ions in this case, acid rain. All right. Now you can actually kind of look at this, and you can simplify this by quite a bit so that you can plug in anything. So we did this kind of by, one problem at a time. But really what would make more sense would be to just rewrite this in that form. So here's what I mean by that. So if we said our pH is equal to log 1 minus log H plus. Well, remember how this is just 0. So really negative log H plus. So if we kind of move things around or just swap the negative here, your negative pH is equal to log of H plus, which we can now just convert and say 10 to the negative pH is equal to your H plus. So 10 to the negative pH. So this sort of gives you a easy to use formula depending on whichever thing you're given. So this is kind of combining a couple skills we've learned into one problem here. So now for like future problems, when they say, how about how many hydrogen ions are in orange juice? You can simply take 3 and just substitute it in here. So you can be like, oh, it's going to be 10 to the negative third. Okay. So you can put that in a calculator if you need to, but it's just, 10 to the negative third is going to be 0.001. It's a thousandth. So there we go. And, if you want to put the unit on here, moles per liter, that's fine. Could have done the same thing over here. Moles per liter. And there we go. So this is using a formula, and you don't even really have to know much about chemistry or this formula or anything to do this problem. That's what's really nice about math. Like, if you've got a formula, you can just roll with it. You don't have to understand much of anything. You're solving for one thing by substituting in a different thing. That's really all this kind of boils down to. But it is handy to resolve the formula to make like future problems easier. So really, if you think about it, if we would have done this at the start, then we could have just cranked out both these really, really quickly. Boom, 10 to the negative 4.5, 10 to the negative third. You could go 10 to the negative 5.6, get this one. 10 to the negative 6.5, get that one. Crank them out pretty quick. So pretty handy to remember. All right. Now what do we have here? So now it says, evaluating logarithmic expressions by changing the base. Now, the other day in the warm-up, I actually showed this to you guys because I think it's just really useful, really helpful to do and understand and know. So I showed you guys how you could use the change of base formula. So I'm going to kind of skip over this piece. You can look through it if you want to, but it sort of shows you why it works. We don't really need it in terms of this. But the change of base formula is what I had in the warm-up there. They may have different letters here. I'm not 100% sure if I use the same ones or not. But basically saying if you want to do log of any base, you can simply do log of the argument divided by log of the base. And you can use any log here. These could be log base 10s. These could be natural logs. Essentially, you want to use anything you can put in your calculator. So I usually would do log m over log b. That's my normal go-to, just using base log out of the calculator. You could also use natural log, and it'll work the exact same. So if you did natural log of m over natural log of b, these are all equivalent. So any of these combinations work. These are the two you usually use because that's what you have in your calculator. So these say estimate the values first and then use a calculator to kind of find the value. So if I'm looking at this, this is saying 2 to what power is 7? Well, I know 2 squared is 4 and 2 to the third would be 8. So I know it's going to be between 2 and 3, right? So like I can look at this problem and I can estimate what that's going to be. But then if I want to actually just evaluate it, I can go ahead and do log of the argument divided by log of the base. So if we do this, boom, 2.8. We can get a estimated answer there. Or sorry, exact answer there. So 2.807. If we go nearest thousandth, yeah, 1, 2, yep. There we go. Now you could guess even further. Like you could sit here, like let's say you didn't know change of base. You could sit here and you could try like 2 to different powers, and you could eventually figure it out. You know what I mean? You'd be like sitting here trying out numbers and trying to get as close to 7 as you can. And eventually you get to the point where you're like, ooh, okay, I'm pretty much there. And, obviously you could keep going until you got exactly 7 or whatever. So that's how you could do it by guess and check, but change the base way faster. Now here, this is kind of a tough one. This is saying 5 to what power is 3? In this case, well, it's not like 5 to the first is 5. So this has to be smaller than the first power. So we kind of know that going in. But once again, I would just go right to my argument here. My calculator. And I would do log of the argument divided by log of the base. And 0.683 if we round that one. All right, I would recommend using change of base formula. Like I said, some calculators do have the option where you can kind of put in the custom base, but I don't ever use it. I have calculators that have it in there, and I do change a base every time because that's what I know, that's what I'm used to, and you don't have to like worry about another thing essentially. So I don't know, both ways do work, so do whatever you prefer. All right, so we're looking good there. Let's see this last problem. So it says, what's the solution of this equation? Express solution as a logarithm and then evaluate, round to the nearest thousandth. All right, so trying to find a solution. So I would look at this and say, well, right now this x is trapped, so I'm going to convert this to a log. So this would be log base 2 of 7 equals x. Once I rewrite it. And at that point, it says use change of base to solve this. So let's do that. That's going to be log 7 divided by log 2, which is the same problem we just did a second ago. So 2.807. And there we go. Pretty simple, pretty straightforward. Don't make things harder than what they are. So this one, same question, different numbers. So right away, I'd start off saying, okay, I need to solve for x. I'm going to rewrite this as a log. So log base 3 of 15 equals x. And then I can estimate, 3 to what power is going to give me 15. So 3 squared is 9. 3 to the third is 27. So it's going to be between 2 and 3. So you can do that kind of stuff. But honestly, you might as well just hop right to change the base because you know it. So 2.465. And there we go. So yeah, change of base today. You'll see some of the other, I'll have some more practice with the other log properties as well. So those 3 properties from yesterday. So you're going to get kind of a mix today. You're going to get some property problems. You're going to get some change of base problems. Lesson summary kind of all mixed in just to sort of make sure you've been able to work with logs in all kinds of different ways.